The main concept in large group was the fact that each electron has its own unique set of 4 quantum numbers. We never gave this a name, but this is called the Pauli exclusion principle. The principal quantum number gets the symbol n, and it can have whole number values ranging from 1 to infinity. Right now on our periodic table, as we have it in the modern day, it only goes up to 7. The lower numbers correspond to lower energy states for our electrons, and the numbers in between, obviously, middle energy states, and the higher the number gets, those are high energy states for the electrons. Remember, this is referring to the probable distance an electron can be away from the nucleus, and it takes more energy to have an electron further away from the nucleus. So modern day evidence of this is visible light spectrum. You can see one here for helium. If you excite helium gas and you look at the light given off by that gas through a spectroscope, you'll see these lines of color. And these lines of color are created by electrons. When they move between the energy levels, they give off light. So this is evidence that these energy levels actually exist. The next quantum number is the orbital quantum number. It gets the symbol L, and it is a range of values from 0 to the value of n minus 1. Once again, smaller numbers correspond to lower energy states. The s orbital, which corresponds to a physics value of 0, is spherical, and it represents one three-dimensional standing wave. That is low energy. P orbital is dumbbell shaped, and that represents 2 standing waves. It takes more energy to make 2 standing waves. Then we have the cloverleaf shaped d orbitals, and we have the really crazy high energy f orbitals. So once again, starting from low numbers and going to high numbers, we go low energy to medium energy to high energy. And remember, the orbital quantum number tells us the shape of the orbital. Okay, the next quantum number is the magnetic quantum number. It gets the symbol M, and it has values ranging from negative L to positive L. And once again, the negative numbers correspond to low energy states for that electron, and the positive numbers correspond to high energy states. And the magnetic quantum number tells us how the orbital is arranged in 3-dimensional space, what axis it's on, x, y, or z. And finally, the quantum number that allows each electron to have its own identity is the spin quantum number. Positive 1/2 or negative 1/2. Remember, in the chemistry notation, it's an up arrow or a down arrow, and positive 1/2 corresponds to low energy, and negative 1/2 corresponds to high energy. So just a quick review of the 4 quantum numbers. Let's do another sample like we did in large group. We have the physics notation here for an electron. Let's figure out what the chemical notation is and what electron it is. So let's go to our quantum table and use the notation that we have. So here's the physics notation up here. Let's do the chemistry notation. Right now, we have 109 electrons to choose from. Quantum numbers are going to help us narrow it down to one specific electron on this whole table. So all we got to do is find what town this electron lives in, and it lives in town number 5. And there are multiple locations for town number 5. We have some in the S block, the P block, the D block, and the F block. But we've narrowed our search from 109 electrons to a much smaller range of 32 electrons. Still, the chemistry notation for N is same as the physics notation. It will be 5. Now, if the L quantum number is 3, that tells us what block we live on. Well, 3 right down here corresponds to the F block. So my chemistry notation is F. And now I can use the M quantum number to figure out what town house I live in. And we live in the -2. And we'll see there's 2 places where we have the -2. And then we got the crazy orbital it makes for the chemistry notation, F zx squared minus zy squared. Now we've got it narrowed down to 2 possible electrons. The spin quantum number will tell us which one it is. We have -1/2, which corresponds to down arrow. We just have to find the down arrow, and we see right there, number 98. This is the notation for the 98th electron. So we have the 98th electron. So what do these quantum numbers tell us? N of 5 That tells us that's a medium energy electron state or energy level that the electron is occupying. And L of 3 is pretty high energy. That's an F orbital. It doesn't get any more high energy than that. Okay, those are the crazy F orbitals that have lots of orientations in three-dimensional space. An M of -2 tells us it's low energy, and it tells us what exact orbital it's in. And an S of -1/2, well, -1/2 corresponds to a high energy spin. So that is what the numbers tell us. We found the identity in the address for the 98th electron. Using the quantum chart, predict the energy state for the 129th electron. When you go to the quantum chart, you'll notice that the electrons stop here at 118. How are you supposed to do 129 if the table only goes to 118? Well, you should know the periodicity of the periodic table by now. We can just start counting and get to 129. I'd start here in the S block and then carry over. But then when I get to 121, we got to bounce down here to the F block and keep counting from there. Okay, we got that segment that got cut out, so we had to come down here. So the 129th electron would be right here, right under the 97th electron. We could start figuring out what the quantum numbers are. So if we have an n value of 4 and 5, well, the next row would be an n value of 6. So physics notation and chemistry notation would both be 6. Our spin quantum number, our L, we are definitely in the F block. So our physics notation would be 3, and our chemistry notation would be F. Right now we see what column we're in, so we can see this corresponds to an M quantum number of -3 in the physics notation, and this crazy notation here, F y cubed minus 3yx squared for the chemistry notation. And then if we look, everything in that row, 65 and 97, is down arrow. So 129 is going to be down arrow. Down arrow corresponds to -1/2. So we'll have -1/2 and down arrow. That's how we find the quantum numbers for an electron that may not be on the chart. So remember in the large group notes, we went to draw a quantum model of an atom and we had an epic fail. Well, let's try it again with a very simple atom, the simplest that can be, hydrogen. First thing we want to do is use our symbol here for hydrogen, and remember that the subscript is the atomic number, and the atomic number tells us the number of protons. So in this nucleus for hydrogen, we know it has 1 proton. All right, now the superscript is the mass number, and the mass number is the number of protons plus the number of neutrons. If we want to find the number of neutrons in the nucleus, all we have to do is take the mass number minus the atomic number. So in this case, we take 1 minus 1 and we get 0. A hydrogen atom has no neutrons. Remember that an atom has to be neutral overall. So if we have 1 proton, 1 positively charged thing, we must have 1 electron, 1 negatively charged thing. So we got to figure out, where does that electron go? Well, we're going to start filling electrons in the lowest energy levels. We're going to start in energy level 1, n equals 1, and the lowest energy type of orbital is an s orbital. So we're going to put an electron in the 1s orbital. The 1 electron that we are going to assign is going in an s orbital, and we have to remember, for the m quantum number, there's only one way to arrange a sphere in three-dimensional space. As a representation of this, I'm going to draw 1 circle underneath the 1s. That represents my 1 type of orientation an s orbital can have. And then also for my m chemistry notation, I'm just going to put a dot for my s orbital representation. Now I'm going to put 1 electron into this orbital, and that 1 electron will be represented with an up arrow because that's the lowest energy. Right now I have 1 electron in the 1s orbital, and that is basically it. That is a hydrogen atom, and now we have to draw it in three-dimensional space. So over here I'm going to fill in the nucleus first. I'm going to put 1 proton and 0 neutrons, and then I'm going to draw the 1s orbital. Now the 1s orbital is just a sphere. We're going to represent it with the circle, and then I'm going to label it. So I'm going to draw a small sphere around the nucleus, and I'm going to label it 1s, and I'm going to put my superscript 1 to represent the 1 electron I have. And that is a quantum model representation of a hydrogen atom. Let's wrap this up. I came up when I told you that that first electron is going to occupy the 1s orbital. Well, how are you going to know where to put the electrons in your quantum model? Well, you're going to follow Hund's rule. And that is that electrons fill the lowest energy orbitals first before they move on and fill up higher energy orbitals. We'll see this with a little bit more detail with the larger atoms we'll make models of. The filling order is basically read off of the quantum chart or off of the periodic table from left to right, top to bottom, just like you'd read a book. And this is the filling order. It's nothing you have to memorize. You just have to use your quantum chart.